So far, we've been talking about features of the periodic table and information that we can find on the periodic table. And so we have been discussing that on the periodic table, several pieces of information are given about each element. So, including the element name, the symbol, which is the one or two letter designation or abbreviation for an element, and the first letter is always capitalized if there are two letters. So the first one is capitalized and the second one is not. Or if there's just one letter, then that is capitalized. And we talked about the atomic number, so which is the number of protons. And we said this is how, or the order by which the periodic table is arranged. So in order of increasing atomic number, ordering of periodic table. Now, we've talked about the mass number, but there is another term called atomic mass that we have not yet talked about, and it is atomic mass that is found on the periodic table. So this is different from mass number that we talked about, which was the number of protons plus neutrons. So the final piece of information that we not need to talk about now is what is atomic mass and how it is calculated. Because the masses of atoms are so small, their masses are not expressed in grams. That is, expressing the mass of atoms in grams would yield such small numbers that it would not be a convenient unit to work with. But instead, the atomic mass scale, is used based on the atomic mass unit, which has the symbol U or AMU. So the atomic mass unit. And so one atomic mass unit, or 1 AMU, is equal to 1.661 times 10 to the negative 24th grams. And so if we needed to express the mass of atoms in grams, we could convert using this conversion factor. But the atomic mass unit scale, or the atomic mass scale, is a relative scale. So this is a relative scale which compares the mass of an atom to the mass of some standard atom. So that would be like saying we compare or use an orange to compare the size of a grapefruit or lemon relative to that of the orange, if we pick the orange as our standard. And so we could say that the grapefruit is twice the size of an orange, or a lemon is half the size of the orange. But the standard atom is the isotope carbon-12, and this was chosen as the standard atom in 1961, and this was after chemists, or before this point, chemists and physicists didn't agree on which standard atom would be used, and so depending upon if you were a chemist or a physicist, you would have different values depending upon which standard atom was used for chemistry and which one was used for physics. And so finally they said, hey, this is foolishness, we should come together and just use one standard atom. And so 1 AMU is defined as 1/12 of the mass of a carbon-12 atom, such that the mass of a carbon-12 atom is exactly 12 AMU. So how do we calculate atomic mass or atomic weight? To calculate the atomic mass or atomic weight of an element, we must take into account the masses of individual isotopes. So we said that isotopes were atoms of the same element that differed slightly in their masses because of different numbers of neutrons. So we must take into account the mass of each of these atoms or isotopes of a particular element and their percent abundance in nature. So that is, if there's a higher percentage of one of these isotopes in nature, then that counts for more of the weight. So we calculate what is called a weighted average, much like, let's say, your overall grade exams are weighted more than a homework assignment. So it's a weighted average. So not everything is equal. So atomic weight is the average atomic mass of an element's isotopes weighted by percent abundance, such that atomic mass is equal to the atomic mass of the first isotope times its percent abundance converted to a decimal number, so percent divided by 100 to convert it to a decimal number, plus the mass of the next isotope times its percent abundance as a fraction. And if there's more isotopes, more than 2, then you can continue on in the same fashion. And so since the isotopes of a particular element differ in their masses, you may have been wondering which isotope was used as the mass for the element on the periodic table. Well, it turns out there's a weighted average that incorporates the masses of all the isotopes, and so together we use these masses and their percent abundance to calculate a weighted average for an element, and that's what's found on the periodic table. So let's look at a specific example. So what is the atomic weight of chlorine? So step 1, so list each isotope, its mass in atomic mass units, and its abundance in nature. So there are two isotopes, chlorine 35 and chlorine 37. And the mass of chlorine 35, the isotope chlorine 35 is 34.97, and that of chlorine 37 is 36.97. And given here is the isotopic abundance or percent abundance. And so what you have to do is divide this number by these percents by 100 to give you a decimal number. And then you multiply the mass of the first isotope times its percent as a fraction or a decimal, and then you do the same for the other isotope and you add those together, and that gives you the atomic mass or atomic weight of chlorine. And so this is what you would find on the periodic table. And then thinking about the rules for significant figures, so here we first multiplied, and when we multiply we look at the value with the least number of significant figures. Both of these have 4, and then so that should be your last digit, as well as this one has 4, this one has 4, and so then this one should be the last digit. And then when we add, so we're adding, then we look at the least number of decimal places, so then we should have 2 decimal places, since this one would have 2 decimal places. So here they've chose to retain extra digits until the end, and so then you would report this as 35.45. Now some periodic tables may have more digits than others, so they may use more value or values with more significant figures than others. But if you're given this set of numbers, then this is how many significant figures you would have or calculated to based on these values. And then another example, so determine the atomic weight of the element copper. So see if you can do that one. So all you would have to do is divide these percents, so these isotopic or percent abundance. So divide those by 100, then multiply each by that value, and then add them up like we did previously. Now, an interesting example related to this topic is calculating the abundance of an isotope, or the percent abundance of an isotope. So previously we calculated the atomic mass or atomic weight, but could we use the atomic weight and the masses of each isotope to calculate their percent abundance or isotopic abundance? Now, this problem with just two isotopes, so this is probably the only one you should expect, because the algebra is not that bad, but we do have to use algebra to solve this particular problem. So if we have just two isotopes, then we don't know their abundance, we can set the percent abundance of one as being x, and then if we know, so the percents equal 100, so let's say that this one was 60%, then we know that the other one must be 40%. But essentially you would say 100 minus 60, and that would leave you with 40. So what you would say is 100 minus x, 100 minus the 60%, which would give you 40, because the percent has to add up to 100. Now, since we convert these into decimal numbers, it's going to be easier to say 1 minus x, so divide by 100, so that we have x and 1 minus x. So we could set for one of the atoms or one of the isotopes x, and then for the other will be 1 minus x. And so just like our formula for before, we need atomic mass or atomic weight is equal to the mass times the percent abundance or isotopic abundance plus the mass of the other times the percent abundance of the second isotope. But in this case, we need the atomic mass or atomic weight of bromine. So did we even read the question? So bromine, atomic mass 79.9 AMU. So that is from the periodic table. We could find that information on the periodic table. Consists of two isotopes, bromine 79 with a mass of 78.92 and bromine 81 with a mass of 80.92. So what is the percent abundance or the abundance of the heavier isotope? So we're trying to find the abundance of the heavier isotope, bromine 81. And because we're trying to find that one, then it makes it easier to just set this one equal to x, because x would be equal to your answer. And then to find, if you wanted to find the other one, then you would have to say 1 minus that value. But essentially what we do is we take the atomic mass, so 79.90 is equal to the mass of the first, so 78.92 times, and maybe I don't need parentheses here, and then times 1 minus x plus 80.92 x. And from algebra, we know that we distribute this term onto everything inside of the parentheses. So this becomes 79.90 is equal to, so we say 78.92 times 1, and then times negative x. So 78.92 minus 78.92x plus 80.92x. And then we can rearrange so that we have our variable on one side of the equation. So that is, we could subtract this value 78.92 from both sides. So 79.90 minus 78.92 is equal to, and that would be equal, if we combine these terms, so negative 78.92x plus 80.92x, we would be left with 2x. So be left with 2x. And so if we do this calculation, we would have 0.98 is equal to 2x. And so then we have to divide both sides by 2. And so x is equal to, if you plug that into your calculator, 0.49. And so this is the percent as a fraction. So x is equal to 0.49. And so if you wanted to percent, you'd multiply that by 100. So that would give you 49%. So the isotopic abundance or percent abundance of the heavier isotope, bromine 81, is 49%. And so then the other one, if you say 1 minus 49, or 100 minus 49, and 1 minus 0.49, that would give you 0.51 or 51% for the other. But again, so all we did, we instead, since we didn't have the percents that we needed, that's what we were trying to find, we set them equal to x and 1 minus x respectively. Now that we have talked about what information we can typically find on the periodic table, let's talk about the actual layout of the periodic table. So how is the periodic table laid out? So the periodic table is arranged into 7 horizontal rows. So 1, 2, 3, 4, 5, 6, 7. So 7 horizontal rows and 18 vertical columns. So columns that go down. And the location of an element within the periodic table is specified by giving its row number and its column number. And we'll come to this in probably the next slide, but rows on the periodic table are called periods and columns are called groups. So rows and columns. So a row on the periodic table, so like I promised, is called a period. And so they are numbered sequentially with Arabic numbers starting at the top of the periodic table. So 1, 2, 3, 4, 5, 6, 7. And a column is called a group or family. And there are two numbering systems that you may encounter. So in one numbering system, we have Roman numerals with the letter A or B behind them, and in the second Roman numeral, we just have them numbered 1 through 18. So here we have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and in the middle of these are B, or in the second way, you just number them So through 1 through 18. So in the first numbering system, this would be group 8A or group 18. And so this method is the traditional US system. So this first method using numbers and letter A or B, and the second one is the more international way of numbering. And depending upon what you're doing, both of them have pros and cons. So which we'll get into a little bit later on. But each vertical column, again, is a group or family. Each family or elements in a group have similar chemical properties. So elements in a group or family have similar chemical properties. So the columns, so every member of the group have similar chemical properties. So elements falling in group 1 to 13, 14, 15, 16, 17, 18. So those this is the international numbering system, or those with the letter A in the US system are called main group elements. So groups 1, 2, and 13 through 18 are those highlighted in red in this particular periodic table. And some of these groups also have common names, so that is non-numerical names. Then those in the middle, or those with the letter B in the US system, are called transition metals. And the inner transition metals consist of the lanthanides and the actinides, which are not assigned group numbers. And so here are the lanthanides and the actinides. So these are usually shown at the bottom of the periodic table. Okay, so your turn. Give the period and group number of the following elements. So period again, row, group is column. So I'll do the first one with you. Let's see. So magnesium. And there should be a periodic table that you can print off from Canvas. So since we're going to be using it for the near future, it would be good to have a copy of the periodic table. So magnesium would be in period 3 and group 2 or 2A. So period 3 and group 2 or 2A. And then I believe the other one was manganese, so that would be in period 4 and group 7 or group 7B. Yeah, so magnesium and manganese. So we said that some of the groups have a common non-numerical names. So what are those names? So group 1A is also called the alkali metals. So these are soft, shiny metals that react vigorously with water. They have low melting points in terms of their physical properties. And even though hydrogen is usually shown at the top of this group, hydrogen is not a member of group. It's not an alkali metal. So excludes hydrogen, even though let's go back. So usually hydrogen is shown at the top. It is not a transition, or sorry, it's not a alkali metal. Good conductors of heat and electricity. So we'll talk about the properties of metals. So metals are good conductors of heat and electricity, and so these are metals, and so they too are good conductors of heat and electricity. They form compounds called alkalis, or basic solutions, when left in contact with water. And it may be interesting to look at what happens when you put these react these alkali metals, so the YouTube videos, so like potassium and sodium and lithium, when you place those in water. So there's a vigorous reaction that occurs. And then group 2A, so group 2A is called the alkaline earth metals. So we have the alkali metals and then the alkaline earth metals. And these are soft, shiny metals, so they also are metals, but they are less reactive toward water than the alkali metals. Then we have group 7 or group 7 or group 7A or group 17, depending upon the numbering system. Group 17, and then group 8A would be group 18. So their name, the halogens, so group 7A or 17, the halogens. And their name comes from a Greek word meaning salt producing. So like chlorine. So when we react sodium with chlorine, we get sodium chloride, which is table salt. And so all in this group, so fluorine, chlorine, bromine, iodine, are diatomic, means we have two atoms of the element and a molecule. They're very reactive and combine with many other elements to form compounds, and they react vigorously with alkali metals, so like sodium, to form salts. Then group 8A or group 18, the noble or inert gases, and so they're described as being unreactive gases that undergo few, if any, reactions, and so hence their name, inert. So they don't typically undergo chemical reactions. They are especially stable as atoms, and so they rarely combine with other elements to form compounds. Okay, your turn again. So identify the element fitting each description. So an alkali metal in period 4, an element in the second period in group 7A, a noble gas in the third period, and a transition metal in group 12, period 4. So pause the video, refer to a periodic table. So I wouldn't expect you to remember these from memorization, but using a periodic table, see if you can find the element that fits this or these descriptions. Okay, so the first one, an alkali metal in period 4. So the group 1 are the alkali metals, and period 4, that would be K, which is potassium. And hopefully you're starting to recognize the symbols of the elements. And then an element in the second period in group 7A, the second period in group 7A, so that would be F, which is fluorine. A noble gas in the third period, so that's group 8A or group 18. Noble gas in the third period, so that would be argon. And then a transition metal in group 12, period 4. Group 12, period 4. So that would be zinc. Okay, so now it's time to separate the metals from the non-metals. And so on the periodic table, there's this bolded line which helps us to separate the metal side from the non-metal side. So elements in the periodic table are divided into two classes by a heavy diagonal line or stairway that starts to the left of B, which stands for boron. Elements to the left of the line have the properties of metals. So to the left, so these in blue have the properties of metals. And note again that hydrogen is in yellow, and those are the non-metals. So hydrogen is a non-metal, even though it's placed here at the top of column 1 or group 1. But the properties of metals, these properties include characteristic luster or shininess, good conductors of heat and electricity, except for mercury, so Hg, which is a liquid. All metals are solids at room temperature. So metals are solids at room temperature except for mercury, which is a liquid. Generally malleable, so that's a physical property, can be hammered into thin sheets, and most are ductile, can be drawn into thin wires. And so drawn into thin wires. Elements to the right of the diagonal line are nonmetals. Nonmetal lacks metallic properties, so those were the ones we described previously. So nonmetals lack these properties. Many of the nonmetals, such as hydrogen, oxygen, nitrogen, and the noble gases, are gases at room temperature. The only nonmetal found as a liquid at room temperature is bromine. And then solid nonmetals include carbon, iodine, sulfur, and phosphorus. So again, we have examples of all three states of matter as it relates to the nonmetals at room temperature. So we have gases, we have one liquid, bromine, and we have several examples of of solids, solid nonmetals. And so we have metals and nonmetals. Now, around the step line, we have these elements that have intermediate properties, so properties between those of metals and nonmetals. And these are called metalloids or semimetals. So some of the elements bordering the step line are called metalloids or semimetals. And so they have intermediate properties, or metalloids have intermediate properties that may resemble those of both metals and nonmetals. So including boron, silicon, germanium, arsenic, antimony, and tellurium. And we said that some of the elements exist as diatomic molecules. So that is two atoms of the same element that are bonded as a molecule. So a diatomic molecule is a molecule that contains two atoms, and so 7 of the elements never appear alone in nature, but instead they appear as diatomic molecules. So like oxygen gas is O2. But to visualize where those are on the periodic table, so hydrogen, so it's found as H2, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So the little mnemonic, so have no fear of ice cold beer is the traditional one, have no fear of ice cold beer. But since some of you may not be of the drinking age, we would say have no fear of ice cold beverages. So have no fear of ice cold beverages to help you remember which ones are diatomic.